All right, so you gave number 2 here a little try. And so what we're going to do is we're going to go through it and we'll see if you've had any mistakes along the way. So it says a bowling ball of mass 6 kilograms is released from rest at the top of a slanted roof that is 4 meters long and angled at 30 degrees as shown above. The ball rolls along the roof without slipping, so rolls without slipping, that's important. The rotational inertia of a sphere of mass m and radius r about its center is 2/5 mr squared. First thing they want you to do is draw a free body diagram. I will make a point. So this one is from 2010. It's still a good question, but the questions now often don't have numbers. So for instance, this one tells me a mass and an angle and a length. Don't expect that in the future. For our tests, they will typically be variable only. Okay, so first thing we need to do is they want us to draw the forces acting on it. And we need to be very particular about how we draw these forces because we want to create a torque equation eventually. So we have mg, which acts from the center of mass downward. We have the normal force acting from the surface perpendicular to the surface. And we also have friction, which is resisting that ball sliding, and that is what's causing it to roll. So those are my 3 forces acting on my free body diagram. They don't want me to resolve mg into components here. They just want me to leave it as mg. So I'm fine with that. All right, so next, it wants me to calculate the force due to friction acting on the ball as it rolls along the roof. If you need to draw anything more, draw it somewhere else. That's fine. Okay, so I'm going to go ahead and rotate my coordinate system. Okay. And when I rotate my coordinate system, it will be accelerating in my x direction, so it'll be ma here. It will also be angularly accelerating, so we're going to sum up the torques and set it equal to I alpha. Now, because it is rolling without slipping, I can link these 2 accelerations that A is equal to alpha times the radius it's rolling on. That's going to allow me to link these 2 equations together. My other unknown that's going to link these 2 equations together is the force of friction, which I'm trying to find. So I'm going to have 2 unknowns really. I'm going to have the acceleration, which I'm going to substitute in there, and the force of friction. So let's get started. So in my x direction, I have this component of mg. They didn't want me to draw it, but I know it's going to be mg sine theta minus the force of friction equals ma. And for my torque equation, mg does not produce any torque. Normal force does not produce any torque. mg because it's at the axis rotation. Normal force because it's not perpendicular to the axis or to that radius. But I do have the force of friction. The force of friction times the radius will equal I alpha. When I have something rolling without slipping, I do need to make the extra effort to say, well, if this is the direction of alpha, I'm going to call that positive. This is the direction of A, I'm going to call that positive as well. All right. So what I'm going to do at this point is I'm going to basically solve and substitute. So I'm going to be able to say that force of friction times R is equal to, they said it was 2/5 mr squared. And instead of alpha, I'm going to do A divided by R. The reason I'm going to do this substitution is I notice I get rid of a lot of my R's. So now I know what the force of friction is in terms of A, but I still don't know what A is. So what I'm going to do is I'm going to substitute in here and solve for A. So now I have mg sine theta minus 2/5 m A equals ma. I should see that the masses all cancel for me. I'm going to go ahead and move all the a's to the same side. So I have g sine theta here equals, and now I'm going to have a plus 2/5 a, so I have 1 plus 2/5. That is going to give me a total of 7/5. Bring it over to the other side, so I have 5/7 g sine theta will give me my acceleration. So when I come back over here, I can say the force of friction is equal to 2/5 times the mass times 5/7 g sine theta. One of the 5's cancels out on me, and so I'm left with a force of friction that is 2/7 mg sine theta. So with this, I should be able to plug in those values. So they told me the mass was 6 kilograms, they told me the angle was 30 degrees, and if I plug those in, I get a force of friction of 8.4 newtons. Okay, so that is part B. Part C wants me to calculate the linear speed of the center of the mass of the ball when it reaches the bottom edge of the roof. All right, well, let's go ahead and set that up, shall we? All right, so now we're on to a part where it's going from one point to another point. That's my clue that I'm going to want to use the work kinetic energy theorem. So I'm going to go from this point here down to this point here. I'm going to set up my work kinetic energy theorem. There is no springs. I'm going to choose my point 2 here as a height 0. So UG2 is 0. It starts at rest. There's no work in because there's no one applying a force. And also work done by friction does cancel out for me. The reason work done by friction cancels out is there's no sliding. So there's no displacement. All that work done by friction is doing is it's splitting that energy into kinetic and translational kinetic energy. I'm sorry, rotational and kinetic translational energy there. Okay, so we have 0 is equal to 1/2 mv squared plus 1/2 I omega squared. So that is my kinetic energy minus mgh, that is my potential energy. Now for the height, I will have to figure out this height over here. And so I'll see that it's 4 times the sine of 30. That will be my height. Because it's rolling without slipping, I can relate these two with v is equal to omega times r. So let's make some substitutions here. I'm going to move this mg over to the other side. So I have mgh is equal to 1/2 mv squared plus 1/2 times 2/5 mr squared v squared over r squared. I see my r squareds cancel. That's a good thing. I also see that the m's are going to cancel for me. I also see that in here, these 2's cancel for me. My goodness. So there's a lot of cancellation going on here. So I have GH is equal to 1/2 v squared plus 1/5 v squared. A half plus a fifth gives me 0.7 or 7/10 v squared. So now I just need to finish solving this. So v is going to be the square root of 10/7 g times my height, which is 4 times the sine of 30. Plug that in my calculator, and you should get a speed of 5.29 meters per second. All right, on to part D. A wagon containing a box is at rest on the ground below the roof, so the ball falls a vertical distance of 3 meters and lands and sticks in the center of the box. The total mass of the wagon and the box is 12 kilograms. Calculate the horizontal speed of the wagon immediately after the ball lands in it. Okay, so the wagon's on wheels, so there's no friction in the x direction. So because there's no net external force on that system, the box and the ball, in the x direction, I can say then that momentum is conserved. So I can say the linear momentum in the x direction before equals the momentum afterwards. All right, so before I have this ball moving with some linear velocity in the x direction and in the y direction. I only care about the x direction, so this x direction, this angle is 30 degrees, so this is going to be v cosine of 30. So I'm able to say that it's going to be my mass times v cosine 30 equals, and then afterwards it's going to be the mass plus the new mass, I'll call it the mass of the cart, going at its final velocity. And so I know this mass, it's 6. I know this velocity, it's 5.29 cosine of 30, all divided by 6 plus the mass of the box and cart combined, which was 12, will give me my final velocity. And so that final velocity comes out to be 2.3 meters per second. There you go.